You can draw Bode plots from a transfer function using approximations, and the approximations are good enough to give you a decent crack at the design. Here are the rules for doing Bode plots from a transfer function. I'm going to be explaining these approximations using transfer functions in the S domain. You could make the j omega substitution if you feel more comfortable doing it in the frequency domain. The first rule is that the DC gain is found by taking the limit as s goes to 0 of g of s. This is no surprise. This is exactly what we've done in the past. A pole at A causes a change in the gain and the change in the phase. A pole at A has a breakpoint at A and then a minus 20 dB per decade slope. On the phase side, it produces a total of minus 90 degrees of phase shift over 2 decades, and that's centered about A. Here's what it looks like on the Bode plot. For the gain, a pole at A is flat with 0 dB until it gets to A, and then it has 20 dB per decade. A decade is a 10 times change in frequency. So this is A, this is 10 times A, here's 20 dB. So the approximation is a straight line that just continues down forever. Looks like a low-pass filter because that's what it is. In terms of the phase is centered about A, a total phase shift of 90 degrees, and it's spread out over 2 decades. So it starts at 0.1 A, 0 up to there, 90 degrees at 10 times A. That's the straight line approximation. Usually people put a little curve in it. It does something more like that. So this is for a pole at A. A 0 at A produces the same effect as a pole at A, except the graphs are reversed. So a 0 at A has a breakpoint at A and then a plus 20 dB per decade slope. So the graph goes like this. It's 0 until we get to A, and then a plus 20 dB per decade. There's 20 dB, there's 1 decade, and the slope continues. The phase has a total of plus 90 degrees of shift over 2 decades, centered about A. So there is A, 45, and the slope does something like this, and the phase does something like that. That's a 0 at A. A pole at the origin has a gain of minus 20 dB constantly and passes through the 1 frequency point. So it looks like this. Here's 1, and it's 20 dB per decade. It's just a line that goes like that. The phase, constant, minus 90 degrees. A 0 at the origin has a gain of plus 20 dB per decade and passes through frequency 1 radian per second with a phase of constant plus 90 degrees. So here's 1 radian per second. So this is a 0 at the origin in the gain, and the phase looks like that. A second order pole is the combination of 2 first order poles. The problem we have is when the poles are complex. When the poles are complex, the system looks like this. It has a total slope of minus 40 dB per decade in the gain. The breakpoint occurs at omega n for the second order system, and it's minus 40 dB per decade. Again, this is my guideline here. I'm going to fix this up a little bit better. And then depending on the damping ratio, the actual curve looks a little different. So if you have a small damping ratio, you'll end up with something like this, and then it ends up tangential to that line. So this might be a damping ratio of somewhere around zeta is equal to 0.1, zeta equal to 0.5, looks something more like that. So we still have a total of 20 dB per decade slope per pole, but when there's a second order pole and it's complex, then we need to look at the damping ratio and the natural frequency. The breakpoint is centered at the natural frequency. The damping ratio determines the shape of the curve around this 20 decade range, 0.1 omega n to 10 omega n. In the phase, I'm going to draw a guideline in again. So we now have a total of 180 degrees of phase shift, 90 degrees for each pole in the second order system. So my guide looks like this. And then depending on the damping ratio, the phase looks different. So a phase curve for a small damping ratio would be very steep. It might look like this. Say zeta is equal to 0.1. A phase curve for a larger damping ratio would be more like that. If you look in the text, there are better examples if you want to make your graph more exact. My position is that you're trying to get an approximation for the design So you use the hand-drawn method to get yourself close, kind of get the feel of what you need to do, and then you can go back and use something like MATLAB that's going to give you a more accurate Bode plot later on. The final piece are the complex zeros or second-order zeros, and I'm going to cheat on this and just say the second-order zeros look like the second-order poles, but in reverse, just like we saw poles and zeros and were in reverse. So a second-order zero is centered at omega n, but instead it has a slope of plus 40 dB per decade, and the second-order phase curve starts at 0. The curve is centered about omega n and has a total phase shift of plus 180 degrees. And so that's all you really need to do a good Bode plot approximation of a transfer function. Remember this, that if a system has multiple poles or zeros, you draw each pole and zero individually on the Bode plot, and then because they're multiplied in the transfer function, you just add those effects in the Bode plot. In the next video, I'll do a couple examples of Bode plots using this method.